Properties of the Poisson distribution. Consider the Poisson distribution, which is lambda to the power n divided by n factorial e to the minus lambda, where lambda is the mean value of n, which is capital N, p, where p is the probability that is much less than 1. Verify that this distribution is properly normalized in the sense that sum over n pn is equal to 1, and calculate the dispersion of n and show that it's equal to lambda. So the normalization condition is that when we go over all possible values of the variable n from 0 to capital N and look at the probability of those values, these probabilities should add up to 1. So in this summation, since e to the minus lambda does not include an n term in it, it can be taken out of the summation. So we have sum n equals 0 to capital N, all possible values of n, lambda to the power n divided by n factorial, where lambda is small because p is much less than 1. So we recall that when you have e to the lambda, the Taylor's expansion for lambda around 0 is e to the 0, which is 1, plus the derivative with respect to lambda, which is e to the lambda evaluated at lambda equals 0 times lambda, e to the lambda second derivative, lambda square divided by 2 factorial, etc. So we get 1 plus lambda square over 2 factorial plus lambda cube over 3 factorial, etc. So basically e to the lambda is, for small lambda values, equal to sum over n equals 0 to infinity lambda to the power n divided by n factorial. So the only difference here is this is an infinite sum and this is capital N. So for large capital N, we can approximate this to be e to the minus lambda, turn it into an infinite sum from 0 to infinity, lambda to the n divided by n factorial, and in that case this is going to become e to the minus lambda times e to the plus lambda, which is 1. So indeed we find that sum over n pn is equal to 1. So that answers part A. Now part B, calculate the dispersion of n. The dispersion of n is deviation from the mean square average value, which is, we know, is n square mean value minus n bar squared, and n bar was defined, it was equal to lambda, so this is basically n square bar minus lambda square, since lambda is equal to n bar, which is capital N p. So our task is to calculate n square bar. So n square bar is by definition sum over n from 0 to capital N, n square probability distribution for n. So this is going to be sum n equals 0 to capital N, n square lambda to the n power divided by n factorial e to the minus lambda. So this e to the minus lambda again does not have an n term in it, so it can be taken out. This is going to be n equals 0 to capital N lambda to the n divided by, for n square, I'm going to use one of the n's to get rid of the n in the n factorial expansion, so it becomes n minus 1 factorial times n. Now we're going to substitute k is equal to n minus 1, and we will assume that since capital N is large, it can be taken to infinity. So if we take this one step further, n square bar is e to the minus lambda sum from, so you will notice that here if you put n equals 0, you already get a 0, so this starts from 1. So basically this is actually n equals 1 to infinity lambda to the n times n divided by n minus 1 factorial, because n equals 0 term gives us a 0. So by substituting k is equal to n minus 1, we can turn this into e to the minus lambda, where n is equal to 1, k is equal to 0, k equals 0 to infinity. And then we have lambda to the n, so that is lambda to k plus 1, and n is k plus 1, divided by n minus 1 factorial, that is k factorial. So if I open this up, this is, it basically has an extra lambda term here, so this is going to be lambda e to the minus lambda, sum over k from 0 to infinity, lambda to the power k over k factorial times k plus 1. So I can write this as lambda e to the minus lambda. If I distribute this sum over the k plus 1 term, the first term I get is k equals 0 to infinity lambda to the k over k factorial, and the second term multiplied with k, of course, and the second term is sum k equals 0 to infinity lambda to the k over k factorial. And now this is going to become, basically this is the, I recognize this to be e to the lambda for lambda small. Therefore I can see that this is turning into lambda e to the minus lambda sum k equals 0 to infinity lambda to the k divided by k minus 1 factorial, if I operate the k on the k factorial, plus lambda e to the minus lambda e to the plus lambda. So if I rewrite that lambda to the k term as lambda times lambda to k minus 1, this becomes lambda square e to the minus lambda sum k equals 0 to infinity lambda to the power k minus 1 divided by k minus 1 factorial plus lambda. So this term again, if I redefine k minus 1 as m here, you can see that this is lambda square e to the minus lambda. When k is equal to 0, m is equal to minus 1. So this is basically m is equal to minus 1 to infinity lambda to the m over m factorial plus lambda. Now since we cannot start from minus 1 because that would give us minus 1 factorial, which is not defined, we have to basically start from 0. So we cannot start this sum from -1. We have to start from 0. And this is going to become now lambda square e to the minus lambda e to the plus lambda. Plus lambda. So that gives us lambda square plus lambda for n square bar. So for the variance delta n square bar, I have n square bar minus n bar square. It's lambda square plus lambda minus lambda square. These will cancel. So I find that the variance of n is indeed equal to lambda, as suggested by part B. The variance of n is equal to lambda. Okay, so we are recalling the Poisson distribution, which is lambda to the n over n factorial e to the minus lambda, where lambda is n bar, which is capital NP. P is much less than 1, n is large, p is small, but lambda is small. Okay, so this can be normalized. So the total summation from n equals 0 to capital N over all possible values of n, if I write this summation, I see that if I take it into e to the minus lambda parentheses, what I have here is the expansion of e to the lambda for a lambda small. It's to capital N, but since capital N is large, we can approximate that to be infinite. So this becomes e to the minus lambda times e to the plus lambda, which is 1. The variance of n is n square bar minus n bar square. N bar was already lambda, so it is n square bar minus lambda square. So our task is to calculate n square bar, which is by definition the sum over all possible values of n squared times the probability, corresponding probability. N squared lambda to the n e to the minus lambda over n factorial. So e to the minus lambda parentheses gives us lambda to the n squared over n factorial, or n over n minus 1 factorial. So I call n minus 1 k, and I notice that n equals to 0 term does not exist. It gives me a 0, so k starts from 0. So it is from 0 to infinity, lambda to the to k plus 1, because k was n minus 1, and for n I substitute k plus 1 divided by k factorial. So this becomes lambda e to the minus lambda to k over k factorial times k plus 1. So if I rewrite this, I get lambda to k over k factorial times k plus sum k equals 0 to infinity lambda to the k over k factorial, which I recognize as, again, expansion of e to the lambda. So these two terms are now lambda e to the minus lambda sum over lambda to the power k minus 1 or I could, instead of doing this, I could also say, since k is equal to 0 will give me a 0 here, this is going to become, the first term is going to be sum k equals 1 to infinity lambda to the k times k over k factorial. K equals 0 gives us 0. So then I substitute k minus 1 is equal to m. So when k is 1, m is equal to 0. So this is going to become m is equal to 0 to infinity lambda to the power k minus 1 divided by k minus 1 factorial, which is sum m equals 0 to infinity lambda to the m divided by m factorial. So basically this part that I have gone through here from this point on is not quite right. So here what I should say instead is what I have done here. So instead of doing it this way, I need to say that this is going to start from k equals 1, because k equals to 0 does not exist. So lambda to the k, because then I'm dividing it, multiplying and dividing by 0, k factorial times k. So for k equals 0, that is 0, and from k equals 1 to infinity, I have lambda to the k times k over k factorial, which gives me lambda to k minus 1 over k minus 1 factorial. So this is lambda square e to the minus lambda, sum m equals 0 to infinity, lambda to the m divided by m factorial plus lambda. So that gives me lambda square plus lambda for n square bar. For n bar square, I have lambda square, so the variance is indeed lambda at the end. So this conversion from k to m should be done after considering the k equals to 0 value in the summation. So that would be the proper way to do this.